Load path analysis in regular versus irregular structures. Welcome to Blueprint to Reality. Today, we're exploring an essential concept in structural engineering: load path analysis in regular versus irregular structures. Load paths are crucial in ensuring that forces acting on a structure are efficiently transferred to the foundation. But how does the shape and symmetry of a building influence its ability to distribute loads? Let's break it down. What is load path analysis? Load path analysis is the process of tracking how forces move through a structure from the point of application to the ground. Every building or structure experiences various loads, such as dead loads, self-weight, live loads, occupants and furniture, wind loads, seismic forces, and thermal stresses. The effectiveness of a structure depends on how well these loads are directed through its beams, columns, walls, and foundations. An ideal load path is one where forces travel smoothly through structural elements without interruption or excessive stress concentrations. When designing a structure, engineers strive to create a continuous and predictable load path to avoid weak points that could lead to instability or failure. Regular structures tend to have simpler and more efficient load paths, while irregular structures present additional challenges. Load path in regular structures. A regular structure is one that has a symmetrical layout, uniform mass distribution, and consistent load-bearing elements. These include simple buildings like rectangular office towers, warehouses, and symmetrical bridges. Because of their geometric simplicity, regular structures offer straightforward and predictable load paths, making them easier to analyze and design. For example, in a rectangular steel frame building, vertical loads from the floors and roof travel straight down through the columns into the foundation. Lateral loads, such as wind or seismic forces, are resisted by shear walls, braced frames, or moment-resisting frames, ensuring that the forces are evenly distributed. Since these buildings are symmetrical, they exhibit balanced responses to external forces, reducing the risk of uneven stress distribution or torsional effects. Regular structures also perform better under seismic loads because the forces are distributed evenly across the structure, reducing the likelihood of weak spots or excessive deformation. Engineers prefer regular structures whenever possible as they offer better load resistance, simpler design processes, and more cost-effective construction. Load path challenges in irregular structures. In contrast, irregular structures have asymmetrical layouts, varying floor heights, complex geometries, or uneven mass distribution. These include curved skyscrapers, asymmetrical bridges, and buildings with large open spaces, or irregular footprints. While aesthetically striking, irregular structures complicate the load path, requiring advanced engineering solutions to ensure stability. One major issue with irregular structures is torsion, where lateral forces cause the building to rotate rather than move uniformly. For example, in an L-shaped building during an earthquake, one wing may experience higher stresses than the other, leading to differential movement and possible failure. Engineers must use reinforced shear walls, cross-bracing, or mass dampers to counteract these irregular stress distributions. Another challenge is discontinuous load paths, where forces must navigate around structural gaps, open spaces, or abrupt changes in geometry. For instance, a high-rise with large open lobbies on the lower floors may experience difficulties in transferring up